Okay, so we are getting ready for the last talk for today, and I'm very glad to say it will be Núria Fagella from Universitat de Barcelona, who will give a talk about boundary dynamics for holomorphic sequences, non-autonomous dynamical systems, and wandering domains. So, please, Núria.
Okay, so good afternoon. Well, I don't know. Thank you for being here after yesterday, for holding on to the end. And so I would like to start by thanking the organizers to allowing me to close the conference, to give this talk, to explain math, but also to say thanks and congratulations to Carsten, which we will leave for the end of the talk, okay? So this is Carsten in the Tropics. Okay, so this is joint work with Anna Benini and Vasily Kiev-Doridou and Phil Ripon and Gwyneth Stallard. And this long title is because I was unable to choose, okay? So let me start by saying that, well, I'm sorry that the topic maybe it's a bit different from what we've been doing, a bit different from what I usually do. This is more local than global, but it comes from some questions that I will explain to you in a second on transcendental dynamics, although the setup that we work with is not necessarily that one. So if we have a Fatou component, which could be of any type that you can think of, the question, the general question or the guiding question is what are the dynamics of the map on the boundary of this Fatou component? So for example, you could ask things, these kind of problems go back already to Fatou, like questions like, does the boundary need to have a periodic point? In particular, this is not known for every type of Fatou component yet, okay? Or, so in this respect, Chetitsky and Zunic proved some very general result with some very interesting techniques for boundaries of basins of attraction of rational maps, proving that periodic points were dense in those. Because you know, periodic points, for example, are dense in the Julia set, but not necessarily on the boundary of a particular Fatou component, right? It could just be approximating them from the outside. Also, you could ask whether if you have a component that is escaping, like a wandering domain or a Baker domain where all iterates go to infinity, you could ask how many points on the boundary, if any, also escape to infinity. Maybe all, maybe only some of them, right? And these type of questions have been in the air for a long time. Ripon and Stallard has worked on them, Baransky and myself and Harke and Karpinska. Also, Lasse told us a little bit about things of this type the other day, Martí Pete and Waterman with their recent results, etc. More general, the question could be phrased as, how do the dynamics inside the Fatou component affect the dynamics on the boundary? Do they have any effect, and which one? Okay? So we actually work in a very general setup. So we will go back to the next slide is about the original motivation, but let me just say up front that we will be looking at something really general, more kind of an analysis problem than a dynamics one, at least a priori, which is to think of sequences of holomorphic maps between simply connected domains, period, okay? So just because I am a dynamicist, I will keep calling this set, Fn of z, an orbit. Okay, take a point, start applying your sequence, and call this the orbit of z, or either inside or on the boundary. But basically, this is all what we are going to ask, that these open, simply connected sets are proper subsets of the plane. Maybe we'll add some hypotheses at some point, which we will talk later. So again, the goal will be to relate the interior dynamics of such a sequence with the boundary dynamics, which still are there to be defined, because what does that mean, right? Okay, so particular cases of this very general setup are, for example, non-autonomous dynamics. So if your sequence Fn can be written as the composition of sequences from un-1 to un of holomorphic maps, right, which is not always the case, but if you can do that, you could consider this as a non-autonomous dynamical system, right? So, to go back. So, for example, think of z squared plus cn, where cn is a sequence of values of the parameter, right? This would be an example that we all could understand, right? And every time you iterate, you apply a different map. So this type of non-autonomous dynamical systems, which also have been around for a long time, depending on how you take these CNs, you open a world on random dynamics, right? Or if you just fix the sequence, then it's more known as non-autonomous dynamics or forward iteration. I mean, you can find these in the literature under many, many different names, actually. Okay, so for example, if you have a skew product, wherever fibered holomorphic map, so that you are fibered over some compact space or non-compact space, I mean, it doesn't matter. So over S1, for example, over the circle, or fibered over C, and you are a skew product, right? So that your first component only depends on the value on the fiber, then you basically have once you fix a point in the base, you have a non-autonomous dynamical system here, right? So every time you fix, for every point on the base, you can write this as the composition of different maps in this fibered holomorphic family, okay? And then you could think of the simply connected sets, who knows? I mean, I'm not getting into that. I mean, you could think of maybe the Fatou set intersected with a fiber, or I don't know. Okay, so a particular case of this, and of the top, of course, is iteration. So if you take every sequence Fn to be the iterate of a single value f, or if you take all the values, all the functions on your non-autonomous dynamic to be the same map, then you are back to iteration. And then you are iterating from a certain set to a sequence of simply connected sets, which if you are thinking of Fatou components, if these sets are periodic, you could think of dynamics on a periodic Fatou component, or you could think of dynamics on a wandering domain if all these UNs are disjoint, which a priori we are never asking them to be. Okay, so if your domains are all disjoint, you could be thinking of the dynamics on simply connected wandering domains, which actually was how we started, okay? But notice that in this general setup, there are no global assumptions on F. It could be entire, it could be meromorphic, it could be whatever. Okay, what else? Well, you could also think of the particular case where every of these open simply connected sets is the unit disk. And this brings us to some classical problems. And having this restriction, you can think of sequences of maps on the unit disk, holomorphic sequences, or compositions of holomorphic sequences on the unit disk, or iteration of a function on the unit disk. So the three cases, sequences, compositions, or iteration, but only considered on the disk. And this is something that brings us or relates very strongly with each of these cases, right, via the Riemann maps. So somehow if you have a sequence of simply connected wandering domains, U1, U2, U3, you can map each of them by the Riemann map, by a different Riemann map, if they are different, to the disk. And therefore, here, by composing, so here is my, let me do this in the case of compositions, for example. If I have F1, F2, etc. here, this will give me a sequence of holomorphic maps, self-maps, of the unit disk on the bottom, right? If this was a periodic Fatou component, we would be iterating a map on the bottom on the unit disk also. Okay, this is the special case. So that's why considering this special case of maps on the disk is especially relevant in all this setting, because somehow, not automatically, we will be able, in occasions, to relate these two things. Okay, so let me start from the beginning, iteration on the unit disk. We all know and love the Denjoy-Wolf theorem, right? This is a classical theorem of analysis, or maybe dynamics. I don't know what Denjoy and Wolf were thinking about, probably dynamics, right? And so what it says, as you very well know, is that unless you are conjugate to a rigid rotation, all iterates inside when you iterate a self-map of the disk converge to some point, which may be in the disk, and then it's a fixed point, or maybe at the boundary. And then it is a fixed point, but in the sense of radial limits, which we will talk in a second, okay? So let me just point out that these maps could be infinite degree. Don't think of Blaschke products, okay? I know that most of us are very rational here, most of you, but try to erase this from your mind for a moment. So if this is infinite degree, you always have at least one point in the boundary where the map doesn't extend. So things can be very complicated in these boundaries, okay? So, well, just think of this P as a fixed point in this special sense that we'll talk. And let me say that this theorem has given rise to a lot of literature on generalizations, on, I don't know, adaptations to more general settings, variations, etc. And let me just mention Marco Abate, or Alan Beardon, or Hans, or Jasmine Raisi, or Filippo Bracci, but I could really go on because there is a lot of literature on this. So just a small warning is that for arbitrary simply connected domains, this theorem is not true, okay? And in Milner's book, you can find an example of that. Okay, so the question is then, okay, the dynamics inside are very well known, very well understood, right? What happens on the boundary? In general, as I said, G does not extend continuously to the boundary, but you can define this boundary extension in the sense of radial limits. And what does that mean? Well, what that means is that if you take, so a radial limit, for those that don't know, is just a limit of your map when you take a straight line towards a boundary point, like a ray, right? That goes to a curve which may or may not land, but it turns out it lands for almost every point. So for almost every point, this map is well defined. So we'll talk about G star of the boundary points, which I will abuse notation and call it G again. And this is the limit, this point here, that we obtain taking the radial limit, okay? So warning, because we are not putting any hypothesis, so that this thing could be inside the disk, and that happens, okay? So, well, if it's inside, that's it. And this is a radial extension, and one has to worry that this really defines a dynamical system, so that almost everywhere. And for that, you just have to check that all the set of points on here where the next radial limit is not, where the radial limit is not well defined, which is a set of measure 0, pulls back to a set of measure 0 here. And this you can do. So basically, just trust me that this is a well-defined dynamical system, up to a set of measure 0, of course. Okay, just for further purposes, let me just say that inner functions are a special case of this. And an inner function is simply a map where this phenomenon, well, it's a map for which all these radial limits are almost always on the boundary. So think about it, just mapping the boundary to the boundary is the proper, it's like the equivalent to a proper map if we were talking about finite degree maps, okay? Or not. So for this inner, for example, if we are talking about Fatou components, it's always an inner function. So this always is the case, okay? Even transcendental. Okay, so even in infinite degree, your map that you induce on the disk in there will be always an inner function, even in this infinite setting here. Okay, so we will restrict to the case where dynamics inside converge to the boundary, okay, simply because the question we want to ask is whether the boundary dynamics follow suit, so also converge to this Denjoy-Wolf point on the boundary. This is our question. How large is the set where this happens? And to So our protagonist today will be this, what we call the Denjoy-Wolf set, which I've written on purpose without mentioning P, because when we move to non-iteration, we will not be talking about this Denjoy-Wolf point, okay? So I've written it like this. We will say that we define the Denjoy-Wolf set as the points on the boundary whose orbit whose orbit is closer and closer to every point in the interior, okay? So points in the boundary which behave like interior points do. Since all interior points go at once, this makes total sense, okay? So observe that this definition, as I said, does not mention the Denjoy-Wolf point, but in this setting, this would be equivalent to say those points on the boundary that converge to P. Okay, so here's our inspiration. Why are we thinking about this? Well, because we found this really interesting dichotomy on the iteration of inner functions. This is fitting for this auditorium. This is a theorem by Aronson, Doring, and Magnet, and we call it the ADM dichotomy, who made this manuscript, published, by the way, here in the Boletim Brasileiro da IMPA or something like that. I don't remember exactly, but it was a Brazilian journal, called Iteration of Inner Functions, okay? And their main theorem, I would say, or one of the main theorems they have in there, because they have plenty of results, a beautiful paper, says the following. The dichotomy goes as follows. If you converge to the boundary fast, which means as fast as this series being convergent, so it means that the modulus of my iterates minus 1 really makes this sum summable, for 1z, although then it's for all, it doesn't matter, then almost every point converges to the Denjoy-Wolf point, okay? So it's like if I go to the boundary fast enough, I carry with me, or I like force the boundary points to do the same. Think of a vacuum cleaner somehow, like, right? So if instead, the dichotomy says that if I don't do that, so, and this is dichotomy because that series either converges or it doesn't, right? So if it doesn't, if this series doesn't converge, so that maybe I'm not converging to the boundary, or maybe I'm converging very slow or slower, then nobody, or sorry, a set of measure 0, so almost all points. In fact, well, the conclusion is that almost every orbit is dense on the boundary of the circle, which in particular means that the measure of the Denjoy-Wolf set is 0, right? Because only a set of measure 0 will be allowed, if any, to converge to the Denjoy-Wolf point. So this is a dichotomy. It's not exactly written like this in their paper. They talk about recurrence, they talk about ergodicity, but you can work a little bit to prove that this really means that almost every orbit is dense, and therefore this statement is what it is, okay? So we talk about the fast convergence case and the slow convergence case. Okay, so this is our inspiration. This is what we would like to extend or see if it holds for our very general setting of sequences or of compositions, okay? So before I go to that, let me just say that, of course, this thing on the unit disk via the Riemann map actually does transfer to periodic simply connected components of the Fatou set, okay? So in language that we understand, of course, using the harmonic measure, right? If you have a simply connected Fatou component, how do you look at the size of these points on the boundary? You use the harmonic measure, which is the pullback of this Lebesgue measure on the unit circle, right? So via precisely the Riemann map and the boundary extension using the radial limits. So the conclusion is then that if I have an attracting basin or a parabolic basin or a Siegel disk or some type of Baker domains, okay, where the convergence to infinity is fast, then I'm in this ergodic case, okay? So almost every orbit is dense, the map on the boundary is ergodic, so the Denjoy-Wolf set has 0 harmonic measure, okay? However, for some types of Baker domains where the convergence to infinity is not so fast, then, and with some conditions I have to say that I don't want to get into, then this Denjoy-Wolf set has, sorry, it's the other way around, excuse me. For these cases, so here, for some Baker domains where the convergence is really fast, right, the Denjoy-Wolf set has full harmonic measure, while in these cases where either I don't converge to the boundary or I converge at a certain rate that is not that fast, then points on the boundary simply behave in an ergodic way. So I have to say that this problem is not closed, so there are still some questions on certain types of Baker domains where, of infinite degree, where really this doesn't seem to be clear in which of these they fall. And this is work that we've been doing for several years with Baransky and Harke and Karpinska, but also Ripon and Stallard have results in this direction. And if you want to learn about all this stuff, I recommend the master's thesis of Anna Joubert, a graduate student of mine, who really put this in a very beautiful way and complete, basically. Okay, so what are the Fatou components that are left? Wandering domains, right? So if we look at wandering domains, definitely the ADM dichotomy does not go because we are not iterating an inner function. We are in this other world, right? Here, by the way, here you have wandering cauliflowers, right? I thought I had to have something parabolic in this conference, no? I mean, if not, how do I justify talking here? So remember, wandering domains need to be in this can only occur in this class with infinitely many singular values, right? So this is very far from rational map somehow. And so in this case, well, just to say that wandering domains can be of many types. They can be escaping to infinity. They can oscillate. We still don't know if you could have bounded orbit wandering domains, as Lasse mentioned. And they are the source of many, many open questions in complex dynamics. But today, we are only addressing this one, right? And as I said, as it's in the blackboard, the ADM dichotomy cannot be transferred because when you map by these infinitely many different Riemann maps, you are exactly at the setting of non-autonomous dynamics of the disk. And therefore, we are looking at these compositions of functions. And here is where we decided to go a little more general, talking about sequences of holomorphic maps on the disk, and why not, most generally, just sequences of holomorphic maps on the open, simply connected wandering domains, which brings us back to where we started, okay? So this is just a little bit of motivation of how our original question relates to all the dynamics that we kind of can picture. Okay, so let's go for the results. So, well, not almost. So the first thing is that before we look at the boundary, why don't we look at the inside, right? Because if we are asking which points on the boundary behave like the interior points, the first thing we have to do is to check if the interior points have some kind of uniformity in their behavior, right? Because if not, the question does not make sense. So Denjoy-Wolf tells you that if you are iterating, they do. But what if you are not iterating? What if you are in this setting, right? So it turns out that interior dynamics can be classified, I'm sure they can be classified in many ways, but we kind of have two types of classification, right? So on the one hand, it's a classification in terms of the hyperbolic distance of orbits, of pairs of orbits. This is what we call hyperbolic clustering. And this classification is only valid for forward compositions, but the other is valid always, which is a classification in terms of whether iterates converge to the boundary or they don't, okay? And this is a subject of a previous paper, but so this is part of our work. And here what we proved, and this is not what I'm talking about today, but it's good to know it, that we have in these two dimensions, hyperbolic clustering, right, or convergence to the boundary, we have like 9 different cases of sequences of this type, which are either all iterates converge Euclideanly to the boundary, and I'll say something later about this Euclidean, or they stay away always, or they oscillate between, for some subsequences they approach it, and for others they don't. And on the other hand, pairs of orbits, either their hyperbolic distance is converging to 0, or it's converging to something that is non-zero, or they actually eventually, they are always the same. So this is like a 3 times 3, no, 3 plus 3, 3 times 2. No, 3 squared, damn it. I mean, what am I saying? Types that are all realizable for these kind of maps. Okay, so, and this is independent of the points you choose. Of course, if not, it wouldn't be a classification, right? So here is where you can start asking, well, so this is like a very rough classification, because converging to the boundary could be, you know, some orbits could be converging to one place, others could be converging to others. So that's really not saying they all go at once, but they do, okay? So the first thing we have to understand, if we want a similar thing to the Denjoy-Wolf point, is that, the Denjoy-Wolf theorem is that you need to even rethink the definitions, because there are no points that we can talk about, right? So these sets are all different. So what is a point in the boundary? It's nothing. We have to replace the word point by the word orbit, okay? So we can think of an orbit in the boundary, and yes, we can wonder whether points in the interior will get all the time closer to this boundary orbit, okay? So we have to kind of change our terminology from points to orbits, both in the interior and the exterior. So the question is, does there exist a Denjoy-Wolf orbit? So do these points always approach the boundary in a certain way? And the answer, and then later, if this is true, we'll ask if the others follow. It turns out it's not quite like that, but this is good enough. So what this says, and this is not difficult to prove, is that if the distance to the boundary is going to 0, so if I have this convergence to the boundary, which I know it's for everybody or for nobody, then all of them do it in the same way. So I don't know yet if they follow any orbit in the boundary or not, but at least the Euclidean distance between the orbit of Z and the orbit of anybody else goes to 0. Okay, so maybe they will be accumulating in places or not. But if I take 2 points in my initial wandering domain, set, open, simply connected set, their Euclidean, as they go close to the boundary, their Euclidean distance will be always smaller. And this is not difficult to prove. It will tend to 0. Okay? Basically, you need to relate the hyperbolic distance with the distance of the orbits to the boundary, with the Euclidean distance between orbits, and with some not too difficult estimates, you can see that this is the case, which kind of makes sense, right? If you think about it, I mean, the hyperbolic distance needs to be contracting. So if one point is going to the boundary, the others have to be clustering with this point, okay? So as I said, I will mention at the end that everything I say could be done in the spherical metric. That's on one hand. And on another hand, this convergence to the boundary can be normalized with the you could do a lot of things in here. Basically, when we say that if one point converges to the boundary, all others do, this kind of doesn't make a lot of sense if this domain is shrinking and shrinking, right? Then you can use other things. We used Euclidean, but because we were most thinking of scaping things, right? But you can use things to normalize. You can use, for example, the hyperbolic metric multiplied by some sequence that compensates for the diameter, like the largest disk you can put in your domain, okay? And probably this could be explored further, I don't know. The plane minus a line, that could be 2, okay? But you could also normalize somehow to, but no, I'm not assuming they are bounded, okay? But again, you could do it with the spherical metric, for example, okay? So let me just say that, well, okay. So we go on with our question. This is just a rephrasing. So now we know that the question makes sense, right? Because since all interior points converge to the boundary together, now we can ask whether this sucks or carries with it a good large part of the boundary orbits. Okay, so in this respect, you can redefine. We already did. Now you see why I didn't want to mention the Denjoy-Wolff point, right? So what I will say is that the Denjoy-Wolff set of a sequence is all points on the boundary whose distance with any point of the interior converges to 0, okay? So this just means the ones that do the same as the interior points. So question, what is the harmonic measure of this set, okay? Good, so is it also a 0-1 result, like in the ADM dichotomy? Okay, so for sequences, so I will state the main theorem. So we will talk about the fast convergence case first, okay? So the ADM dichotomy had 2 parts. It said, if orbits inside converge very fast to the boundary, then the Denjoy-Wolff set has full measure. It carries everybody. So let's look at this case first. In this case, we have a full generalization of this. So if you have a sequence of holomorphic maps on the disk, and this series converges, again, same condition, then for almost every point in the boundary belongs to the Denjoy-Wolff set, which means that it does exactly the same as the interior points. In other words, the measure is 1, okay? So this is what it says. If the convergence is fast enough, everybody follows, or almost everybody follows. And let me just say that this is, so if you put here, instead of Fn, the iterates of an inner function, this is exactly the first part of the dichotomy, right? So a special case. But not only. It turns out that this is a special case of the really general theorem that we can prove, which is the following. It says, now let's go to the maximum generality. So holomorphic maps from simply connected open sets. So if, and we are going to put this hypothesis, which I don't want you to worry about it, okay? Full radial extension. I will say something about this in a second, but let's forget it for a moment. The condition here, it's very interesting because it seems to depend on the geometry of the set, okay? On the simply connected sets. So here I've put the worst case in this statement, but I will comment on that. So the worst case is if the sequence converges a little bit faster than the other ones, right? If this distance to the boundary, to the 1/2, is still summable, then again, the measure of the Denjoy-Wolff set is full, okay? So it carries everybody with it.
Sorry, what was the hypothesis of the previous result? What maps were you looking at? It wasn't.
Here, I was just concentrating in the disk for a moment, okay? But it turns out that this 1/2 that I've put here is just not to scare you, okay? Because 1/2 really is an alpha. And this alpha is depending on the alpha harmonic measure condition of the boundary, which is a geometric thing. And I'm not going to get into the definition for those that don't know, but let me just say, if the boundary is C2, this alpha is 1, okay? If the worst case, however, is if I have an inward cusp. And in that case, alpha needs to be 1/2. So this alpha really is a quantifiable quantity that depends on the shape of the domain. So the weirdest, or let's say the less nice the boundary is, or the more like a cusp it is, the faster you need to go to vacuum with you everybody, okay? That's basically the...
Full always means
full harmonic measure.
You never need everything.
I never have everything. This, clearly, we only have results in terms of measure, okay? Alpha only depends on you, okay? On all of them. Alpha depends on the sets that you are looking at. Okay, so for sequences, this 1/2 is sharp, Okay, so we can build an example where you really need this 1/2, because if you don't converge with this speed, and this is precisely an example with cardioids. Okay, so cardioids that map one to the other, and there you can show that 1/2, you need this convergence, or the result is not true. But this is something we've done with cardioids on one next to the other. We don't know if for wandering domains, this is really going to be a sharp condition or not. Okay, maybe it's not. Okay, so this is the main theorem that we have, which we are satisfied because we believe this really generalizes the first part of the dichotomy, okay? And you cannot do better than this, I think. Okay, what about slow convergence, the second part? Well, we are not so successful there, but it's not our fault, it's just that it's not true, okay? So, I mean, that's what it is. So, what about slow convergence? So, if you have that the distance, the iterates converge to the boundary not so fast, can you deduce that the Denjoy-Wolf set has harmonic measure 0? And the answer is no, at least for sequences or compositions. We don't know about wandering domains, but we believe that with latest results from Lasse, we'll be able to kind of transfer our examples. So probably for everybody, but I'm not saying anything about that. Why do I say no? Well, because we can build examples where, simple compositions of Blaschke products where everybody inside tends to 1, but, and slowly, right? But still, you have a positive measure set that converges to this 1, okay? Those are simply maps on the unit disk. Or the same, but the opposite. Everybody goes to 1 slowly, and there is almost everybody is dense, almost every orbit is dense. So basically, any behavior can happen when the convergence is slow, okay? And I'll go to that, okay? No, because for example, well, actually here, I think we proved that the measure is positive, but not full. So, okay, but I'm actually not sure here. So let's see now that putting some hypotheses, we do have the dichotomy. So let me just say that to build these examples, it's kind of fun. Huh? I mean, it's non-trivial. We have been using like Borel-Cantorelli methods and these shrinking targets construction. So this is interesting, I think. Okay, so in fact, one wondered when we saw this zoo of possibilities, we thought maybe the Denjoy-Wolf set could be empty. Maybe, there's no orbit in the boundary that kind of does the same as the interior orbits, right? And indeed, it can. So for sequences or compositions, yes, it can. So we have this example, this very simple example of Mobius transformations of the disk, for which all orbits inside tend to 1, but then nobody tends to 1, not even 1. So it's like even the orbit of 1 just gets away from itself, So the Denjoy-Wolf set actually can be empty, okay? So it could really be empty. Okay, we don't know if this is possible for wandering domains, but again, we don't know if these things will be able to be transferred or not. Oops, sorry. What? What happened here? Oh my God. Here. Are the orbits then in this example? I don't really know, but I do suspect so, okay? So I don't remember how the proof went because we had so many examples that at the end I'm a little confused. But I think they are. Okay, so let me just give you some hope on this respect, on Juan's question, which is putting some extra hypotheses, at least we can prove that there is a dichotomy. Okay? And this gives us some hope that with this hypothesis, a 0-1 result will be possible. So, well, it is, no? But maybe more in general. So this is only valid for compositions. We don't know about sequences. So if you have a non-autonomous dynamical system like this in the very general setting, etc., and we have these following conditions, and you only should worry about the contracting one. The rest just says that points should be going to the boundary, okay, that we understand. This is the third, sorry. The fourth is that, the first one is that, what was this? that, this is kind of an inner condition. So you are asking that these are somehow proper maps. So for example, if you were thinking of holomorphic maps on Fatu components, this would be immediately true, okay? The third is the same. You are just asked that everybody converges to the boundary, as we know. And this is the restrictive one, is that you need to be in the contracting case. So you need the hyperbolic step to be tending to 0. So you need the hyperbolic distance between pairs of orbits has to be going to 0. In that table, you need to be on the contracting row, okay? So if this is true, then we can prove that the Denjoy-Wolf set has either full or 0 measure. So this really makes us think that maybe there is a hope for a full ADM dichotomy, in this case, of inner functions that are of the contracting type, okay? But for now, we haven't explored further than this. Okay, so
these are three, does all three conditions have to be satisfied, or just one of them?
no, 3 conditions. So what we can prove is that you have an inner, in the sense that we all understand, radial limits belonging to the boundary, inner sequence composition of this type, of the contracting type, then it's 0 or 1. But you need the 3 conditions to be satisfied, okay? Interior points going to the boundary, contracting hyperbolic metric, and contracting hyperbolic distance, excuse me, and inner, okay? So just to finish, so this kind of finishes our work on the dichotomy itself. But now what we want to finish is to say, listen, we always say that, you know, interior points are very big and they carry with them boundary orbits sometimes. Well, it turns out that boundary orbits can also carry the interior one somehow. So this is a result that is new even for iterates of inner functions. So this, we have not found this anywhere, and says exactly this. So imagine I have a point in the boundary, okay? Oops, this is a typo, okay? So this is not f to the n, this is fn. So both this and this are fn, obviously, okay? So imagine you have a point on the boundary which basically stays in the boundary or converges to the boundary or whatever. So this really only says, if you have a set of positive harmonic measure that behaves in the same way, in the sense that the Euclidean distance of the orbits converges to 0, on the boundary, right, everybody in the interior has to do the same. So in other words, if a large set of boundary points behave in the same way, then this set must be in the Denjoy-Wolf set, so that every interior point has to follow suit, which in particular tells you that at most you will have one such set. Okay, so the philosophy of this result is that if there is a positive measure set on the boundary that behaves uniformly, it needs to be in this Denjoy-Wolf set. Okay. So this is basically all I wanted to present today, and let me finish with some final remarks. So the first one, that most results can be proven with a spherical metric. Okay, this is obviously useful for unbounded domains, where going to the boundary could mean nothing Euclideanly. Stronger versions for wandering domains we don't know, right? We went to this very general level, so kind of we are now expecting that this will be able to be applied in many settings, but for now we've just proven the tools, okay? And I don't know, maybe when you put all the restrictions that come with wandering domains, maybe you can prove stronger things. For now, we don't know. What else? As I said before, when we have not explored what happens when orbits do not converge to the boundary. So imagine that they don't. And then, of course, you should expect something like recurrence, or what do you expect? Because what does it mean, recurrence, when your sets are different, right? In a disk, it makes sense, but anywhere else, if anybody would want to look at this, we would have to rethink the definitions, the ergodic definitions, etc. What else? This is, as I said, related to some new results of Martí Pete, Rempe, and Waterman, where they talk about maverick points, these points that the wandering domain goes to infinity, but the boundary points don't, and they prove that this has measure 0. So it's not exactly the same definition, but it's related, and I don't want to get into it. And let me say that you can extend some of these results, especially the classification, to multiply connected domains, and this is work of Gustavo, there we go, Gustavo Rodriguez Ferreira, and he has some nice papers on multiply connected wandering domains where orbits converge to the outer boundary of the domain, right? And then the classification, hyperbolic clustering, and all what I've talked about is kind of generalizable, okay? It depends it's interesting because it depends on the eventual connectivity and, well, on the geometry of the domain again. So these are basically the final remarks, and I just wanted to, something I told you I would say is this boundary extension. Well, you shouldn't worry too much about that, but because for all the examples that you can think, it's true. But let me just say that this would mean that our maps on top, you can extend them to the boundary radially in a way that it's compatible with this extension on the bottom. Okay, so for example, if your domains are Jordan curve, or not even that, if your domains have points on the boundary that are only uniquely accessible, then this extension is always true. Or if the map extends continuously to the boundary, even if the boundary is absolutely horrifying, that's also true. It extends to the boundary, okay? So it's not really a big restriction unless you are in the super very general setting, okay? So I think, thank you for your attention. That's all I wanted to say, and happy birthday, Carsten.
Great. Questions?
Sigma, yes, yes. So they, sorry?
Which is equivalent to the
Exactly, exactly, yes.
So it is just criterion for dissiperativity, conservativity.
Exactly, exactly, exactly. You described it.
So I guess if you consider these two products, so with some measure on the basis and on fibers you have these domains and have more fibers hyperbolic measures, you can ask similar questions whether there is an invariant measure which is.
I think so. I mean, we haven't explored this. We haven't explored this, but this is clearly one way to go, right? So especially in the case we have not looked at, which is when orbits do not converge to the boundary, because that's when this measure plays a role, okay, to show that the boundary dynamics are ergodic, etc. Okay, recurrent and conservative, etc.
It would be natural generalization.
Yeah, that could be nice. I totally agree.
Did you say what outer boundary means? I may have missed it.
These are all simply connected. So outer boundary equals boundary. But what I said about outer boundary is that Gustavo has extended these results to wandering domain, not for general sequences.
What's the definition? I don't think I know.
What, Gustavo?
Literally mean outer, like in the sense of outer.
Yeah, because the thing is that, if your domain can fit a sector in the outer part of a certain angle, then your alpha, sorry, I don't remember now, it's like pi over, so it's related to how wide this sector is. And in particular, if you can fit a circle, a tangent circle at every point on the boundary, then the alpha is 1, okay? So that's why a cusp like this is like the worst that you can have. But you can use the Milosh inequality to show that 1/2 is the worst. Okay, so that even this has alpha equals 1/2. Sorry? This is Lumini, yes. But I have another one. So this is, that's nice, huh? So, so let me, sorry. So this is Holbeck 2013. We all look a little younger, right? Little, no, not much. So, well, I just, well, many of us are here. I found especially nice to have the 2 graduate students of Carsten here, right? Ashla and Luna. And I don't know, Marti Pete here, Bodil, right? Well, and so many other people. Adam, look at you. Okay. Paul York. Yeah, and Bogusha, and I don't know, this was a very nice picture, so I have several others, but. Okay, so I think we'll finish here, but stay tuned, because I want to show you, I want to give some surprise to Carsten, okay? So we finish here, and now I want to do a couple of things, so you have to bear with me for 5 minutes or maybe a little longer. So I have several things for Carsten, okay? We have, because Christian and I have been some collective work here. So the first thing I want to do is to try to, let me see if I can manage this. Let's see if somebody is over there. If not, we'll do the others until, sorry? So no, okay, not yet, fine. So let me just quit this for a moment. Well, then, since I see that this person has not connected yet, I hope he will. If not, no, okay? But let me just show you a couple of things. So the first thing I want to do is to read a letter, a short letter that Bodil Branner, oh my God, I don't want to be there, wait. I don't want to be there all the time, so let me just quit this, okay. So the letter is from Bodil, okay, and I think I have to read it. She sent it especially to be read to you. I wanted to do it yesterday night, but the environment was not for that, okay? The caipirinhas were fantastic, but somehow I don't think they would have helped to listen to the letter. So it said, "Dear Carsten, I am so pleased to know that you are being celebrated this week in IMPA. I don't remember exactly when we met the first time, but surely it was after 1986 when I returned to Denmark after my visiting professorship at Cornell. At that time, you were a student at Aarhus University in Jutland, while I was at the DTU in Copenhagen. We were about to find a topic in complex analysis for your master's thesis. Your advisor at Aarhus University suggested that you contacted me. Perhaps your topic could be in holomorphic dynamics. What a lucky suggestion. This is how you became my first student in holomorphic dynamics. From the very beginning, you had to work very independently on the topic since our workplaces were not close. Not every student would have mastered that, but you really thrived. Thrived? Nowadays, we could have connected easily by Zoom, but this was not possible at that time. After this, you became my first PhD student in holomorphic dynamics. You still in Aarhus and I in Copenhagen. You defended your thesis during the summer school in Hillerød, real and complex dynamics, in Denmark in '93. And several participants in the birthday conference met each other for the first time then and there. We know, right? For many years, Adrian Douady organized holomorphic days in Paris. You have continued that tradition by organizing holomorphic workshops at this rather remote place in Denmark, Sommienstationen. As employed, well, okay, Thanks a lot for having created these possibilities to meet, collaborate, and create friendships. Thank you, Carsten, for our long friendship and our collaboration. I send the best wishes for you and all the participants in your birthday conference with love, Bodil. Okay. Okay, second, I want to say a couple of things myself. I just want to say that, I don't know, I prepared here very briefly. I also was one of those that met Carsten in Hillerød and in many other conferences. So this is a picture I see at basically every conference I go, because you are always in the front, right? So that's how... So this is really a picture that, and also usually with the hat. When I saw this picture, I thought, this is Carsten, right? So, well, you defended your thesis, etc. We met, many of us met there, what became our mathematical family, right? Bodil, Adrian, etc. Thank you for your hospitality. I've stayed at your place from the very young days. I've met your family. This is a friendship that I appreciate very much. And although we've never been able to work together, we've shared a graduate student, okay? And I still don't lose hope, although the years go by, you know, so I don't know. And just I feel very lucky, like many of us here, to have shared your generosity with your mathematics and with your life, to be a role model, like a good balance between life and work. And, you know, your modesty and your, you know, I don't know, working in these very hard problems and having so many insights and questions and curiosity. So I think this is what I would pick out to remark from you, okay? Good. And now I want to show a couple of things from other people that also wanted to say something to you. So if I get out of here, should I close this? No, but what is this? But I have this, here, thank you. There is a mouse helping me here that works independently. So while we wait, just in case that the connection comes, I just want to show you
Hi, Carsten. As you can see, winter finally came to Toulouse. I hope you're all having fun in Rio, and I wish you a happy birthday conference. Hi, Carsten.
Okay, that's it.
As you can see, winter finally came to Toulouse. I hope you're all having fun in Rio, and I wish you a happy birthday conference. Hi, Carsten. As you can see.
Okay, okay. Next one.
Hi, Carsten. Congratulations. I hope you are enjoying the conference. I'm sorry I missed that very special event because of this little excuse sitting on my lap, but my mind is there certainly. I would like to thank you so much for all the motivation, support, and friendship throughout the years. It means really a lot to me. I'm very happy, and I feel so lucky that I had you and Nuria as my supervisors. I'm really grateful. I wish you fulfilling, active, joyful, so many years in the field. Also, happiness and good health. All the best. Hi, Carsten. Congratulations. I hope you're enjoying the conference.
So is this video, yeah. Okay. And finally, so it seems that, okay, so I think Hubbard wanted to connect, but he hasn't, okay? So if he ever does, I don't know. So I think we will end the session by something really nice that Pascal prepared for you, okay? And this is this is what it is.
Hi, Carsten. I want to say to you happy birthday. The conference is really great. I can follow on the channel. I hope you have a good time with the fest and you enjoy.
Okay, and that's it. So I want to finish thanking all the organizers, especially Luna, which now will say some words, and also to the technical people that has been here giving support for all these days, okay? Sorry? Sorry? Ah, yeah, that's true. We decided yesterday between Caipirinha and Caipirinha, we would specially thank Luna's husband, who has been the one that made this possible, okay? So I think we should clap for him.
Well, I would like to thank you all, and thank you, Carsten. I would have, when I started my PhD, I would never, ever expecting to finish it, to do a career in math, to organizing this after 15 years later. I don't know, I don't remember. And thank you for the ideas, discussions, patience, very much patience, and everything. Thank you very much. Mein Dank. And thank you all for coming. Yeah, as I said, I hope we will repeat. And thanks.